Hello everyone. This session is on deriving the dynamics of inverted pendulum on a moving cart by using Lagrangian Euler method. So before we start the derivation of inverted pendulum dynamics by using Lagrangian method, we will review some of the basic concepts. That is, let us start with the potential energy. So potential energy is the energy possessed by the system when it is at rest. So if at all the system is at an elevated height, say h, and it is having a mass m, then the potential energy is given by m g h, where g refers to the gravitational constant. And then next, kinetic energy. So kinetic energy is defined as the work that is required to accelerate the system of a particular mass, say m, from the stated velocity, say v. So in classical mechanics, the kinetic energy is represented as kinetic energy is equal to half m v squared. So next we will see about Lagrangian. So Lagrangian, the natural form of Lagrangian is defined as, say, L is equal to kinetic energy minus potential energy. So the equation of motion can be just derived by directly substitution or using the Euler-Lagrangian equation. So the Euler-Lagrangian equation is given by tau is equal to d by dt dou L by dou theta dot minus dou L by dou theta, where tau is nothing but the n-dimensional vector of generalized forces, n-dimensional vector of generalized forces, and theta is an n-dimensional vector of generalized coordinates. So it represents that theta represents the joint variable. So if you have for a manipulator, if you have two joints, then the size of this vector will be 2 cross 1. Now let us derive the dynamics of inverted pendulum on a moving cart. So the inverted pendulum, it has been a great platform for engineers to develop different types of applications, including segways or the self-balancing scooter, walking robots, etc. Let us consider the inverted pendulum model here. So here you can see you have a moving cart with an inverted pendulum hinged on top. The pendulum, it is a stiff bar of length, say L, and it is supported at one end by a frictionless pin. So let us consider the mass of the pendulum to be small m and the mass of the cart to be capital M. So the motion of this system, it can be defined by the displacement of the cart from the reference point. That is, you can just use the displacement of the cart from the reference point. So let us say y, and the angle the pendulum rod makes with respect to the vertical. So this one, that is theta, right? So you can define the motion of this particular system by two coordinates. That is, one is the displacement of the cart from the reference point. Let me denote it as y, and the angle the pendulum rod makes with respect to the vertical, that is theta. So instead of theta, that is instead of using y and theta, in place of theta, you can also have consider the horizontal distance of the bob, that is this distance. Let us take this as say y1. You can also consider y1 or the vertical distance of the bob. So this distance, that is z2, right? So instead of theta, you can also use the horizontal distance of the bob or the vertical distance z2. So this is very important, like as because this system has only 2 degrees of freedom. So dynamics in terms of this should be in terms of these generalized coordinates. The equation of motion for this system, it depends on both the cart motion as well as the bob motion. First, let us consider the moving cart. The potential energy associated with the cart when it is at rest is equal to 0. The kinetic energy of the moving cart, let us denote it as say T1, will be equal to half into the mass of the cart is denoted as capital M into the velocity. So if at all we have represented the position of the moving cart from the reference as y, then the velocity will be y dot square. So as you know, velocity is a vector representing change in position. So we have just taken the position of the cart from the reference point to be y1, sorry, y. So the velocity will be y dot square, right? Then coming to the bob. So the bob is confined to move in horizontal and in vertical direction. So the potential energy will be equal to m, that is the mass of the bob into gravitational constant into the elevated height. So the elevated height here, as you see in the figure, it is given as Z2. So to derive for Z2, let us illustrate this separately here. So here, this is the vertical distance and this is the pendulum. And from the vertical, it is having an angle theta. So this distance we have taken it as y1, and this elevated height, this is z2, right? So if this angle is theta, so this elevated height will be if the length of this the L is the length of the pendulum, so this distance will be L cos theta, and y1 will be equal to L sin theta, right? So here mgz2, which means it is equal to mgl cos theta, right? So next we'll just get the kinetic energy. So kinetic energy, it is half mass of the bob. So let us, sorry, this is small m, half m into, so as I have told, a bob is having both horizontal and vertical motion. So m into the horizontal distance. So what is the horizontal distance? It is moving from the reference. So here, as you can see, if you take the total distance, so let us take the total distance from the reference to be y2, right? So it should be y, if the position is y2, then the velocity should be y2 dot square, right? Y2 dot square plus the vertical distance. So the vertical distance, it is z2 dot square. So z2 dot square. Okay. So we can just write this as what is y2. So from the figure it is clear y2 is nothing but y plus y1. So we know what is y1. So we have y1 as L sin theta. So y2 is equal to y plus L1. Y plus y1. So y2 is equal to y plus y1. So we can write this as y2 is equal to y plus L sin theta, right? So what would be y2 dot? So we want the velocity to determine the kinetic energy. So y2 dot will be equal to y dot plus L cos theta into theta dot, right? Similarly, you can write for Z2 also. So we have already seen Z2 is equal to L cos theta, right? So we have Z2 dot Z2 dot is equal to minus L sine theta theta dot, right? So the total kinetic energy of the system, that is total kinetic energy of the system, which is represented by T, will be equal to T1 plus T2, where T1 is the kinetic energy of the moving card and T2 is the kinetic energy of the ball. So we can write this as T is equal to, what is T1? We have already got T1 as half into capital M into y dot square plus, what is T2? Half into M. Just by substituting the values of y2 dot and z2 dot, we will be getting half M into, let me write it here, y dot plus L theta dot cos theta the whole square plus L squared theta dot square sine square theta, right? So you can just expand and solve this. So you'll be getting half into M y dot square plus half M y dot square plus 2 y dot theta dot into L cos theta plus L squared theta dot square, right? So we'll be actually getting L squared theta dot squared into cos square theta. So we will be taking that common. So cos square theta plus sin square theta becomes 1. So we'll be getting this as our expression for total kinetic energy. So the total kinetic energy is half m y dot square plus half m y dot square plus 2 y dot theta dot L cos theta plus L squared into theta dot square. Now we have to get the Lagrangian. So the Lagrangian L is equal to the difference between the total kinetic energy of the system minus the potential energy. So the total kinetic energy of the system we have already got. So the equation is half m y dot square plus half m into y dot square plus 2 y dot theta dot L cos theta plus L square theta dot square, right? This is the total kinetic energy minus the potential energy, total potential energy. So the potential energy of the cart is 0 and the potential energy of the bob, we have got it as mg L cos theta, right? Mg L cos theta. So on rearranging this, we'll be getting a half into, we can just combine these two terms. So it will be half into m plus m y dot squared plus, we can write it as m L cos theta y dot theta dot, that will be the second term, plus half m L squared theta dot square minus mgl cos theta, right? So this is your Lagrangian. Now we have to get the equation of motion by applying this Lagrangian in the Lagrangian-Euler equation. So as discussed earlier, the Lagrangian equation of motion for the system is represented by two equations as we have taken two coordinates. So here it will be d by dt of dou L by dou y dot minus dou L by dou y is equal to F, where F is the applied force to the system as shown in the figure here. So F is the applied force to the system. So d by dt of dou L by dou y dot minus dou L by dou y is equal to F. This is for the cart, and for the ball it is d by dt of dou L by dou theta dot minus dou L by dou theta is equal to 0. So there is no force applied to the ball. So here the force applied is 0 here, right? So these are the two equations of motion. Now for the derived Lagrangian, let us determine dou L by dou y dot. So we have to differentiate the Lagrangian equation with respect to y dot. So as you see in this equation, there are only two terms which has y dots, that is the first term and the second term. The third term and the fourth term doesn't have y dot. So they on differentiating with respect to y dot, these two terms will become 0. So let us first differentiate the first term with respect to y dot. So we will be getting half m plus m is a constant there. So half m plus m into, on differentiating this you will get 2 y dot. So this 2 and 2 will get cancelled and you will be getting m plus m into y dot, right? Then differentiating the second term with respect to y dot. So these terms are constant. So we will be getting ml cos theta theta dot, right? So now as per the equation of motion, we also have to determine d by dt of dou L by dou y dot. So that would be m plus m y double dot plus ml cos theta theta double dot, right? Next, we also want to determine the minus dou L by dou y. So we have to determine dou L by dou y. So dou L by dou y, as you see here, there is no term in the Lagrangian equation which contains y. So simply dou L by dou y will be equal to 0. Now let us do the same for the second equation of motion. So dou L by dou theta dot. So as you see here, theta dot. So you have theta dot in the second term and also theta dot in the third term. So other two terms on different, the first term and the last term on differentiating becomes 0 there. So dou L by dou theta dot will be ml cos theta y dot plus ml squared theta dot, right? So d by dt of dou L by dou theta dot will be equal to ml cos theta ml cos theta y double dot ml cos theta y double dot plus ml square theta double dot. So this will be d by dt of dou L by dou theta dot. So next in the equation of motion we also need to find dou L by dou theta. So dou L by dou theta will be equal to, as you see here, the first term doesn't have a theta and the second term also don't. Yeah, here the second term you have a theta, so call ml cos theta y dot theta dot, and so the second term and the last term has theta. So on differentiating, you'll be getting m, so it should be, sorry, minus ml sine theta. The differential of cos is minus sine, so others are constant, right? Minus ml sine theta y dot theta dot. Then differentiating this last term with respect to theta, you will be getting plus m g l sine theta, right? So I'll just make it neatly in the next slide. So just by substituting all the terms, whatever we have derived into the equation of motions, we will be getting these equations, uh, two equations for the inverted pendulum on a moving card. So m plus m y double dot plus ml cos theta theta double dot minus ml theta dot square sin theta is equal to f, and ml cos theta y double dot plus ml square theta double dot minus mgl sin theta is equal to 0. So by taking two generalized coordinates y and theta, these two are the dynamical equation governing the system, that is inverted pendulum on a moving card.